stresses, that's right. Yeah, we did two stresses due to torque for two different types of cross sections. The first one is for circular cross sections, hollow or solid, and the second one was for thin-walled tubes of any shape. And so now we're going to do an example at the only place that those overlap with a hollow circular cross section, and we're going to do it for two different thicknesses of the wall and just see how they relate to each other. So this is a comparison of the techniques for circular cross sections and thin-walled tubes for hollow circular cross sections. So we'll think of the calculation so the calculation, assuming a circular cross section, is going to be the one that we're going to treat as the true answer. And we'll compare the results for a thin-walled tube and see what happens as the wall gets thinner and thicker. So thin-walled tube approximation to that. Okay, so we'll first do it with so here's our tube. And the torque we'll apply to it will be 10,000 Newton meters this way, 10,000 Newton meters this way. So that's a couple. And the analysis we're going to do is going to be, it doesn't matter where along the length of this tube we look because internal torques are all the same. But we're going to look at two places, the outer wall and the inner wall. So I'll first do the outer wall is going to be A, the inner wall is going to be B. And our cross section has an outer radius of 0.4 meters. And an inner radius of 0.35 meters. Okay, so what we have here is a wall thickness that's I guess about 10%. Definitely that wall isn't way thinner than the range where we would trust that thin walled approximation. So let's see what happens here. So for the circular cross section, our formula is, and this is, I set this up sort of nice for us. X, Y, Z. These points A and B are right along the Z axis, so we're not going to have to worry about any rotating of coordinate systems. So in this case, tau xy is equal to negative torque times rho over I sub p. And I sub p is pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. This is a formula I gave you. And that is, I don't know. Can someone calculate that? 0.016. Do you think that's repeating? And that's meters to the fourth. The internal torque at that point, well, we can cut it right at the location that we want, so we'll be skipping all this stuff out here, including that torque. So over here we have a torque of 10,000 to the left, and that's counteracted by this internal torque. Well, if this is going this way and that's going that way, those have to be equal magnitude. So the x component of the moment equation says the internal torque is positive 10,000. At A, the point A in the cross section, so that's at the outer wall, rho is equal to the outer radius. Okay, that makes sense. So rho is equal to 0.4. And so torque at A is negative 10,000 times 0.4 divided by 0.01664. And what do you get for that? Okay. And that is pascals. That's such a gigantic internal torque and such a small stress. It's going to break. It's not going to break with that. You would think so with that torque, but then you look at this and that's tiny. No metal is going to break with a stress like that. The reason is that's a huge radius that I gave it, you know. The radius is this big, so that it's like a culvert. Like you could totally climb through that. Yeah. So, and remember, the farther away you get the material from the center line, the more resistant the internal torques it is. Right. That's right. It's thick. Yeah. Okay. So now at B. Tau xy at B. Right. Yeah. So we got negative 10,000. Rho in this case is 0.35. Divided by 0.01664. And what do you get for that? Okay. So we get a significantly bigger stress at the outer wall than at the inner wall. I said that the assumption of thin-walled tubes is based on saying that when the walls are thin, the stresses are the same throughout the wall thickness. You can see that's not true here. But I think what we're going to see is when we make the thin-walled assumption, we're going to, so there's not going to be any distinction between the points A and B because that's what the whole assumption is based on. But we're going to get a value somewhere in between here. That tells you, you know, that'll tell us how far off we are by assuming this is a thin-walled tube. Any questions about where we're going with this?
So the steps that we're going to do prior to this one now is just for explanation.
Yeah, it's just to see, we're just trying to get a sense for how much information we're throwing away by assuming things have thin walls and how thin, like how much the quality of your answers depends on how thin the walls are. Like, was that a thin-walled tube? I mean, the wall was, you know, I mean, there's a big chunk cut out of the middle, but unless you are really just trying to get a very rough estimate, choosing a single number in between those two is not giving you a very accurate idea of what the stresses are inside there. But, you know, I mean, it's off by, so let's say that, let's say that we get an answer of 225 or something, negative 225,000 pascals. Then even though, you know, we're 15,000 pascals too big there, 15,000 pascals too small there, we're still within 10% for our answer, you know. So it's like, it's not great, but as far as just trying to get a ballpark figure that you could then compare to finite element results or something, like depending on your application, it's, if that's the only way you can do a calculation, it might not be so bad. In this case, we have a better way to do the calculation. But the point of the thin-walled things is most of the time you don't, because most of the time you're not lucky enough to have a circular cross-section. And if you have a tube that's not a circular shape, there's only one way to do this calculation. And you have to know whether you can trust treating it as a thin-walled tube or not. You know what I'm talking about? Whenever I ask that question, I only look at people who I know what I'm talking about. Um, okay, so now we'll treat it as a thin-walled tube. And so our formula for that is now we're going to assume that the stress at A is equal to the stress at B. And so this single stress value that they share is equal to negative torque divided by 2 times the wall thickness times the area inside that median line. So let's start getting this information together. The torque is the same as it was before. The wall thickness is 0.05. If that's the cross section, the median line is this. So that's a circle with a radius of, this isn't 0.05. Oh yeah, it is 0.05. And then this would be 0.375. That's the radius to that median line. And so in this case, it's easy to calculate the area inside that median line. So it's just going to be pi times 0.375 squared. What do you get for that AM? 4418. Okay, so tau x y is equal to negative 10,000 divided by 2 times 0.05 times 0.4418. And what do you get for that? 354. And that's pascals. So almost exactly in between those two values, I think. It's not exactly in between in general, but in this case, it's pretty close. So you could use that to calculate like a percent error at these two extremes. You know, it would be something like 14,000 divided by, say, 240,000. Can someone calculate? I mean, it's less than 10%, more than 5%. Any questions about that? Or the thought process? I guess the thought process is what I'm really trying to get at here. Okay. Yeah, or 7%, right? Okay. 7%. Okay, so now let's do it with a 1 centimeter radius and see how much better it gets. So we'll do a cross section where the outer radius is still 0.4. And the inner radius is 0.39. And first I'll do the calculation for a circular cross section. What? 0.39. So that wall thickness is 1 centimeter instead of 5. So first I'll do it A. That's the outside. So rho is equal to 0.4. We need the polar moment of inertia again. That's equal to pi over 2 times 0.4 to the fourth minus 0.39 to the fourth. And what's that? Zero zero 3873 meters to the fourth. And so tau xy at the outer edge is equal to negative 10,000 times rho 0.4 divided by 0.003873. And what do you get for that? Okay, so this time we got a stress that was right around 5 times as big as we did in the first case without changing the torque. Why is the stress so much bigger? Thinner walls mean there's a lot less material to support that load, and so the stress is bigger everywhere. Now at the point B, rho is equal to 0.39. I sub p is the same. So tau xy at the point B is negative 10,000 times a rho of 0.39 divided by that same value of I sub p. And what do you get for that? Okay, so you can see percentage-wise, the stresses at the inner and outer walls are a lot closer now that we have those smaller walls. Okay, so now when we make that thin-walled assumption, we're going to get a value that's in between those two somewhere. And I mean, basically, these only vary by like 2%. So if it's right in the middle, it's going to be an error of around 1% compared to where before the error was 7%.
But what if you not have the luxury of making it such a thin wall too?
Yeah, well then, there are a million things that we don't have the ability to calculate from what we're doing in this class, and then that's just one of those things, you know. Like if you have, yeah, or what if it's not a tube at all, you know, like what if you have a square cross section and you want to calculate the stresses due to the torque? We just can't do that. But if you have a fairly thin-walled tube, then our answers, you know, this gives you a sense of how close our answers are going to be. Okay, so now we'll assume thin-walled. The thickness this time is 0.01. How did I draw that so thin? Our median line is right in between the inner and outer. And so this time, that radius is 0.395. And so the area inside the median line is pi times 0.395 squared. What's that? 0.49. And so now plug all this into the formula for the stress. You get negative 10,000 divided by 2 times 0.01 times 0.49. And what do you get for that? And so what we get is basically 1% error compared to 7% error, because that wall is thin enough for this assumption to be closer to correct, you know. Okay, so the thinner the wall of the tube and the bigger the diameter of the tube, you know, basically like the bigger the diameter is compared to the wall thickness, the better this approximation is. Any questions about this?
So it's the physical, the bigger the tube is, and the thinner the wall is, the more accurate.
That's right.
So it's not the ratio between those two.
It's the ratio. Yeah, you want that ratio to be big or small, or whichever order you gave them in. You want the diameter to be way, way bigger than the thickness, percentage-wise, fraction. Right, but not if it's a 11 centimeter diameter. Okay, now we've done all these. I want to do one more example problem, but let's go back and just refresh our memories about the limitations of all of these different stresses. You know, before each. So here's a review of stresses in beams. So we know that the total stress is equal to the sum of the stress tensors for tension, compression, bending moment, shear force, and torque. So one by one, let's go through the requirements for these. Okay, so what were the requirements for tension compression? Sort of a trick question, I guess. I didn't give any for this one. This is pretty universal, although I think it might go off if there's a really drastically changing thickness along the length, you know. But I didn't say anything about this, so we'll just say no restrictions. Okay, so the first one I talked about was for the stress tensor due to bending. What were the restrictions here? It had to be prismatic. Yep. One more, I think. Yeah, so straight. And it can bend a little bit, but if it's very sharply curved, the more sharply it's curved, the worse your answers are going to be. Okay, so this one, I'm not even, anything works. This one, let's talk about some acceptable cross sections. That, 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 um, hollow is fine. Okay, so all those cross sections, we can calculate the stress due to bending, as long as it's prismatic and straight. And there's a million more, that you don't see that one as much. Okay, now what about the stress tensor due to shear force? This one is pretty severely limited. I didn't even talk about restrictions. I only gave the two cases that we could do. Yeah, so all we can do are rectangular. And the other one is circular, but with circular, we can't even do it everywhere. We can only do it along the neutral axis. Why would we even care if we can do it just at this one location on the cross section? That's at least that has the usefulness of being where you have the maximum shear stress due to shear force. But that doesn't mean that it's that doesn't mean that when you calculate all the stresses, that's where you're going to have the maximum shear stress that you find by doing the principal stresses and stuff. Okay, so what are some acceptable cross sections here? Yes, very good. But one thing I should point out is, and remember the rectangular one, tall and thin is better. You could do a hollow one of these. I guess that's sort of an exhaustive list of the cross-sectional shapes that we can do for shear force. And then the last one is the stress due to torque. What are the requirements there? Circle? Yeah. So yeah, we can do this. We can do hollow circles, and you can do that, and and so on. Obviously, we can do simple thin-walled tubes. All right, so out of this whole world of cross-sectional shapes, where we have different requirements for all of the things, what are the shapes? Where we can calculate stress if we have non-zero tension, bending moment, shear force, and torque. Okay, so if we only have one or two of these, then you don't have as much of these requirements fighting each other, But what if we have all of those? Are there any shapes where we could do all of those? Yeah, and the rectangle has to be hollow. Because it has to be thin-walled. So we kind of have, I think there's only two options. A thin-walled rectangular tube, or a circle at the neutral axis only. In what way? Oh, are common? Oh, well, that's good to know. I guess I didn't know that. I mean, I know, so we can't do this with I-beams, which is too bad, because that's a pretty common thing in construction. But yeah, that's good news, because I don't think, really, I would guess that the construction of these doesn't have anything to do with what we can calculate and what we can't calculate. It's just sort of luck of the draw. It's probably just easier to manufacture. And also, those are shapes that have a pretty good resistance to torque, pretty good resistance to bending, and so on, without requiring a ton of material. Okay, so let's do one of these. We have 8 minutes. Just kidding. These take forever. Good thing what? Okay, so let's say we have a force over here of, that looks like 5,000 newtons. And let's say that we have, at the midpoint, downward force of 4,000 newtons. And there's also a couple there in this direction of 2,000 Newton meters. And let's say the whole length, 1 meter. We'll ignore the weight. Not because it would be any harder to put the weight into this; it would be pretty easy. But if we're dealing with a hollow rectangular shape, unless this goes about a mile back into the board, the weight is going to be pretty insignificant compared to those forces.
It could go a mile into the board.
It could, except I'm about to tell you it doesn't. Yeah, exactly. Okay, so cross section has a height of 5 centimeters. And a width of 0.02 meters. And a thickness of 3 millimeters. Can you guys picture like an old steel bike frame? Think of those like old heavy, or like modern ones, like a steel bike frame. You know how, so those are all tubes. You know how thick the frame tubes are on a pretty common, so thin, you can't believe it. Like, I mean, less than a millimeter thick. On those, they feel like tanks, and they don't flex much unless you really bang them hard into something. Yes. So this thickness is 0.003 meters.
Isn't that due to the length of the tubes themselves are not that long, so they can not deform under huge loads?
Yeah, you're right. Yeah, the longer they are, the thicker you'd want to make them. Okay. Uh-huh. Yeah. Well, you know what the sad thing is about that? Like at some point they just stopped. They said like we're not going to keep making bikes look weirder and weirder, and so there are limitations on how. Like actually, if they did a Tour de France no holds barred, everyone would ride recumbent bikes. But that would look pretty stupid. Um,
I wonder if you can make a bike out of that piece of carbon. Just one slab.
it'd be pretty flexy, I think. That's okay. So first, let's think about what the mass of this would be. Or actually, let's think about the weight. So let's say that this is steel. Well, the volume is the length times the area. So what would the area be? That would be 0.05 times 0.02 minus 0.04 4 times 0.014, right? So what's the area there? 384. Okay. And the whole length is a meter, so the volume is the area times the length, which is this meters cubed. You know there's a weight minimum for like the Tour de France too on bikes. They can make bikes way lighter than what those guys ride. They're just afraid that there's going to be a lot more crashes and stuff if they try to really push the envelope with how thin things are. So it's like your bike isn't allowed to be less than 15 pounds or something like that. And they actually sell bikes that are 11 pounds just for regular Joes, you know, but in the Tour de France, you're not allowed to ride it. Okay, so that's the volume, the density of steel. This is different than, oh, that was in dynamics, the thing where everyone put density for the row vector. Density is not a vector, and the density for steel is 7,000 kilograms per cubic meter. So the mass is 7,000 times that volume. So what do you get for that? 2.69 kilograms. And so the weight is, what's that times 9.81? 26.37 newtons. And so that's why in most deform problems, they just leave the weight out. It often is not a significant contributor. Okay, we'll start this next time. So we're going to calculate the stress due to the tension, due to the bending moment, shear force, torque. Oh, and I didn't say where we're calculating this, did I? I meant to. So we're going to do it. We're going to calculate the stress. So at the midpoint this way, between, well, like at the quarter point here. And let's do it halfway between the neutral axis and the top. Okay. So these two lines are where we're going to calculate the stress. Okay, that's all.